I want to continue our discussion of circular motion and forces in circular motion. But in this segment, I want to focus on gravity in circular orbits. As with a lot of this stuff, as with anything forces related, Newton is really the hero of this segment. Now, there's a man named Kepler, Johannes Kepler, and he also played a significant role in figuring out the motion of the planets. But it was really Newton who figured out why the planets did what they did, who figured out a mathematical model for gravity that accurately described the motion of the planets. You know, these days we spend a lot of time looking like this, right? But back before the invention of the cell phone, people looked up quite a lot. They looked up at the stars in the evening quite a lot. And people noticed that there are these regular patterns that just happened all the time, right? The stars, you know, they come up in the east, they set in the west. They move around a little bit throughout the year. All the same stars are not visible through the entire year, right? They change throughout the year. But at the same time, on the same date, every year, the same stars are up there. You know, so take a constellation like the Big Dipper. Probably most of you could identify the Big Dipper out there. And, you know, in the summer and the spring, the Big Dipper is pretty high in the northern sky. And in the winter and the fall, then it's a little bit lower in the sky. And that happens every year. If you want to know where the Big Dipper is going to be in the sky, you know, on April 3rd next year, well, guess what? It's going to be in the exact same place in the sky that it was last April 3rd, as it was the April 3rd before that, as it has been for basically forever, right? Very predictable. Nobody knows who discovered this, right? The ancient peoples just knew this because they spent their evenings staring at the sky. Every year, same pattern, same thing. The sun, totally predictable, right? In the summertime, it's a little bit higher in the sky. In the wintertime, it's a little bit lower in the sky, but it rises in the east, it sets in the west every day. Totally predictable to the ancient people. Except, when you look up at the night sky, there's a billion dots up there. More than that, billions of dots up there. Billions of pinpricks of light. And every one of them follows this pattern, right? Every one of them is in the same place, on the same date, at the same time, every year. Except for 5 of them. There are 5 dots up there in the sky that are not in the same place every year. And the ancient peoples, they gave them a name. They called them the planets. And they call them planets based on the word for the wanderers. So there's these 5 wanderers up there in the sky, and they don't follow the pattern. You know, Jupiter might be over there in the sky this April, and next April, it might be in a totally different part of the sky. It might be way over there, right? So there's these 5 dots. Out of the billions of dots up there, there's 5 of them that don't do the same thing every year. They seem to move somewhat erratically. We have this word in the English language, mercurial. It means ever-changing and unpredictable. Mercury, in particular, just goes all over the place. Sometimes it heads east, sometimes it heads west. It does all kinds of weird things. And so it was an open question. To ancient peoples, it was an open question. Is it just that we haven't found the pattern? Or is there actually no pattern? Right? Historically, the planets have been named after gods, right? Because gods are capricious and unpredictable, and they just do whatever they want, right? And so this question bothered thinkers throughout history. Is this a problem that can be solved and we just haven't figured it out yet? Or is there literally no solution? So the ancient peoples wondered about this. The Greeks wondered about this. People have always wondered about this. Until the 1600s, right? In the 1600s, actually, Kepler came along, Johannes Kepler. And he made a really important discovery. Well, he made 3 important discoveries. We're going to talk about one of them here in a little while, in a little bit more depth. But Kepler figured out that the planets move in ellipses, okay? And he figured out that they speed up a little bit when they get a little closer to the sun, and they slow down a little bit if they get a little bit farther from the sun. And he figured out that how long it takes for the planet to orbit the sun is related to how far away it is from the sun. And that the farther away a planet is from the sun, the longer it takes to go around the sun. So Kepler figured it out, right? Like, for, all of human history, people have wondered, can we figure this out? And one human, his name was Kepler, he figured it out. He figured out that now we can predict the motions of the planets. Now, Kepler's laws were what we call empirically based. In other words, he saw the data. He was actually working for a wealthy astronomer named Tycho Brahe, and he actually had years of data on the positions of the planets. And so Kepler was able to see this data and work with it, and he was able to fit these ideas to the past and use that to predict what would happen in the future. Now, he didn't really have any idea why the planets moved in ellipses, why they sped up when they got a little bit closer to the sun, or why the amount of time it takes to orbit the sun is related to how far away they are, right? But he knew that that was true. And so he came up with these rules, and finally, people could predict the motions of the planets. And then Newton came along, and he was able to figure out a mathematical model that predicted Kepler's rules. And so, between Kepler and Newton, they finally solved this riddle. And now, if you want to know where Jupiter's going to be, on April 5th in 2046, guess what? You just go online and you look it up. It's there, right? And it's there because of the work that Kepler and Newton did in the 1600s. So, Newton was a really interesting guy. He, as I've said, he's kind of the hero of all of this force business that we've been talking about. He was born on Christmas Day in 1642. He was very premature. It was said that he could fit in a quart jar. So he was very premature, small. He was a sickly child. His father died before he was born. When he was still a young child, he was sent to live with his grandparents. He lived in Northern Europe, in the present-day country of the Netherlands. Between the ages of about 12 and 17, he was able to attend a pretty good school. He learned Greek, he learned Latin, and he had a pretty good basis for mathematics, most likely. After that, he actually went to Cambridge in England, and he studied there for a few years. Shortly after finishing his bachelor's degree, Cambridge shut down because of the Black Plague for 2 years. So we can identify with him in this moment, I think. So Cambridge got shut down for 2 years, sent everybody home. This was before Zoom. So what did Newton do? Well, you know what? He kept working. He kept working on his own. When the plague ended and things started rolling again, Newton came back. He'd spent these 2 years thinking about things on his own, and he was ready to go. He had the origins of these ideas, so many of these ideas that we've already talked about in this class, and many of the ideas that we're going to talk about for the remainder of this class. In his life, Newton invented calculus. He was the first person to figure out that sunlight can be broken down into the Roy G. Biv, all of the constituent colors. He was the first person to describe the tides. Why are there 2 high tides a day? Right? And ancient people knew it was related to the motion of the moon, but why 2? Why not just 1? That was Isaac Newton who figured that out. What else? The list goes on and on and on. The thing we're talking about here today, though, is his theory of gravity, his mathematical model of gravity. And, his real genius was recognizing that the force that makes this tennis ball fall to the ground, the thing, prior to Newton, we didn't have this notion of a force. So this thing, whatever it is, the thing that makes this ball fall to the ground is the same thing that makes the moon orbit the Earth. It's the same thing that makes the Earth orbit the sun, that makes Jupiter orbit the sun, that holds our galaxy together, right? This was Newton's breakthrough. Because, we're sophisticated 2020 humans. Maybe that's not mind-blowing to you, that it's gravity that pins me to the ground, and the same thing makes the moon orbit the Earth. But think about it from the perspective of somebody living in the 1600s. This is a revolutionary idea, right? Remember Aristotle. Aristotle said, a rock falls to the ground. Why? Because it's of the earth. It wants to be with its stuff. Okay. And why do the planets move, according to Aristotle? Well, because the gods are influencing them, right? So prior to Newton, we had this idea that different motion had different causes, and that it's not necessarily all related. But Newton came along. He said, "No, these are all forces, and this business with the rock falling and the moon orbiting, that's the exact same thing. Exact same thing." And there's this possibly apocryphal story where Newton was hit on the head by an apple, and he had this flash of insight. Well, first of all, flashes of insight don't really happen that often in the world. Newton thought about this stuff for years and years and years. In fact, his contemporaries described him as being totally reclusive. They'd pass him in the hallway. He'd be so deep in thought that he wouldn't even respond to them. There's these stories of him working for days on end, and they'd have to bring him water and convince him to eat because he was so absorbed in thought. Okay, so a few years of total focus and attention, and then a flash of insight at the end. Okay, this story is probably not really true. It's based on a quote from one of his contemporaries who wrote a biography that was published in 1752. And in this biography of Newton, written by William Stukeley, he wrote, "The notion of gravitation came into his mind, occasioned by the fall of an apple as he sat in a contemplative mood." Okay, so not quite an apple whacking him on the head, but still, again, we see that his real genius, well, he did a lot of genius things, but the real breakthrough he had was recognizing that the thing that pulled the apple to the ground is the same thing that makes the moon orbit the Earth. Okay, so Newton published this idea, his universal law of gravitation. We'll get to the equation here in just a minute. He published this in a book called the Principia de Mathematica, and it was published in 1687. And in that book, he proposed the following thought experiment. And I think this thought experiment is good. It helps us see how he was able to realize this connection between the fall of an apple and the orbit of the moon. And so the thought experiment that Newton did here is he said, okay, here's the world. That's the Earth. And I'm gonna build a tower here on the Earth. There we go. I'm the king of the world. I have my tower. I'm standing on it. Been working out. I throw an arm. Okay. I take a rock and I throw the rock off of my tower. What does it do? It does that. That's projectile motion, right? We studied that a few chapters ago. Okay. I do some push-ups, work out a little bit more. I can throw my rock a little harder. So now what does it do? Oh. That's interesting. It goes a little farther, doesn't it? Part of why it goes farther is because I've thrown the rock harder, right? And so it's just going to travel farther before it hits the ground. But part of why it travels farther is that now it's gone so far that the curvature of the Earth has curved away from it a little bit, right? So that's part of why it went a little bit farther. What if I throw it even farther? Okay, now I'm really working hard. Oh, maybe it would make all the way to there. What if I threw it really, really, really hard? It might go all the way around and whack me in the back of the head. It just might do that. And so we see here that really projectile motion and orbits, they're not really totally different things, right? It really is just sort of an extreme example of throwing a rock. An orbit really is an extreme example of throwing a rock. How fast do you have to throw a rock in order to get it to orbit? Well, that's a good question. Let's answer it. So here's a little picture here of this situation. And here we see the Earth. And of course, weight always pulls towards the center of the Earth. Well, we know that a force pulling towards the center of some circular motion is providing the force that causes centripetal acceleration. And so it's causing this object to accelerate in a circular fashion. We can actually do a calculation and figure out how fast I have to throw that rock. So here's an example. How fast would I have to throw a rock to get it to orbit right at the Earth's surface? This is a thought experiment. This would be hard to perform in real life. For the sake of this problem, let's ignore air resistance, buildings, mountains, trees, all the kind of stuff that makes this really impractical. Okay, let me clear off my board and we're going to do it. Okay, here's the Earth. Zoomed out a little bit. Here's my rock. And I don't know, let's just say it's moving in this direction here. There's my velocity. Okay, so free body diagram for my rock at this point. Well, gosh, only one force, right? As I indicated in that previous slide, there's the weight. It's going something like that, right? The weight always pulls towards the center of the Earth. This is a circular motion force problem. Let's define our coordinate system. We always make positive towards the center of the circle. And so now we can do sum of the forces in the x direction equals mv squared over r. There's only one force on this rock. It's in free fall, right? And that's its weight. So let's go ahead and see what we get there. So this is just w equals mv squared over r. Moving along, mg equals mv squared over r. Cancel, cancel. And we see that v equals the square root of g times r. Okay, well, let's just plug in our numbers and see what we get. And I've given you the radius of the Earth there, 6.37 times 10 to the 6th meters. And I run my calculator, and I get 7,900 meters per second. Something like 8,000 meters per second. Pretty fast. Not ridiculously fast. That's 16,000 miles an hour. Humans have created objects that are going that fast. So anyway, kind of an interesting thought experiment. If I can throw a rock 8,000 meters per second, then what goes up does not necessarily come down. Okay, so Newton had this realization about gravity, and he took it a little bit farther. He actually proposed a mathematical model for it. And so the mathematical model that he proposed is given here. That two masses will attract each other, and that the force of the first mass on the second is equal to the force of the second mass on the first. Well, we already learned that. That's Newton's third law, equal and opposite forces. So here we see this diagram. These two masses are attracting each other. Here is his equation, g m1 m2 over r squared. What are these parts? G is this constant. It just keeps all the units straight. M1 and M2 are the two different masses, and R is the distance between their centers. So we have to be a little bit careful. R is not necessarily the radius of whatever round thing is in the problem. R is the distance between the centers of these spheres. Now, Newton didn't have the benefit of symbolic algebra. I think symbolic algebra is one of mankind's greatest inventions. And Newton was working prior to its refinement. And so, it would not have looked like this at all. If you were able to get a copy of the Principia de Mathematica and check out his version of it, well, it would be in Latin, and it would be with words, right? So he said, the force is proportional to the product of the masses and inversely proportional to the square of the distance between them. Now, the gravitational constant here, that is our constant of proportionality. And Newton didn't know what that was at this time, right? This number right here was not discovered until the 1700s. A man named Cavendish was able to measure the gravitational force between a couple of lead spheres. And so Cavendish was able to come up with the first good number for G. Prior to Cavendish, all we had was that they were proportional, but we didn't know the proportionality constant. Okay, let's apply this. A typical bowling ball is spherical, weighs 7 kilograms, and has a diameter of 22 centimeters. Suppose two bowling balls are right next to each other in the rack. What is the gravitational force between the two? Magnitude and direction. Okay, so here are my two bowling balls. Each has a diameter of 22 centimeters, and if they're right next to each other, then this distance here is one diameter. So this is 22 centimeters, and it tells us that the mass is 7 kilograms. Okay, great, let's just run this calculation. Okay, so there's our setup. Let's run our calculator. And we get about 7 times 10 to the negative 8th, it looks like. Okay, so, 10 to the negative 8th newtons. Oh, heck. That's a pretty small force. I think it's measurable. It is, right? I mean, it's maybe like the weight of an eyebrow hair. Something like that, right? Definitely measurable. I said Cavendish was the first person to measure this value G. He was able to do that by measuring the gravitational attraction between two lead spheres. I think one was about 9 kilograms. The other was 3 or 4 kilograms. So, in the 1700s, Cavendish was able to measure a force that was on this order. So, definitely measurable. Noticeable by a human? Probably not, right? If you're holding this bowling ball here, it's got a weight of something like 70 newtons, right? So I'm holding a 70 newton bowling ball. I'm not gonna notice a 7 times 10 to the negative 8th Newton force sideways if it's right next to something, right? So not something a human would notice on their own, but something that one could measure if one was very careful and motivated to do so. Okay, so Newton publishes this gravitational, his universal law of gravitation in 1687. It's a huge triumph, along with a whole bunch of other stuff that he published. But finally, people can make these predictions using some mathematics, and now we know why this mathematics works. So that's all good. Again, we've got the 5 planets, right? We've got Mercury, Venus, and we're not counting Earth. Earth is obviously visible with the naked eye. But so in Newton's time, there's 5 known planets other than Earth, right? We've got Mercury, Venus, Mars, Jupiter, Saturn, right? So those are the 5 planets visible to the naked eye, and nobody knows who discovered Jupiter, right? Because the ancient peoples have just always known that it was up there, right? So these 5 planets are visible with the naked eye, and nobody knows who discovered them. And finally, after millennia of not being able to predict their motion, now finally we can. And so, also, like I said, Newton had refined the telescope, so people were making better and better telescopes. In the 1700s, there was a husband-wife team, William Herschel and his wife Caroline, and they had built this enormous telescope. Herschel had to climb up a big old ladder made out of wood. It had some mirrors in it, and Herschel had to climb up this ladder, and he would sit way up there on the end and peer into the eyepiece. The eyepiece was way up at this end because there was mirrors, and it was a reflecting telescope, Newton's idea. And so he'd go up there, and he'd peer into the end, and he'd make these observations, and he'd call out to his sister, who would record them all down. In 1781, they announced that they'd discovered a new planet. And it was Uranus. And it turns out that under just the right circumstances, Uranus is visible to the naked eye. But at the time, this was not known, right? And so Uranus is discovered, finally, by William and his sister Caroline Herschel. And William wanted to name it George. I really wish he had gotten his way. But the King George at the time, he wanted to name it after King George. But the Royal Astronomical Society would not have it, and so we are stuck with Uranus, unfortunately. Anyway, end of the 1700s. Now we've got another planet. Okay, this is awesome. So, good telescopes. Now we've got 6 planets, not counting Earth, visible to the naked eye, and folks are keeping a close eye on Uranus, and everything's looking good for a couple decades, and then people started to notice something. And what they noticed is that Uranus's orbit kind of did this, and Newton's prediction said, no, it should have done this. Right? So the orbit of Uranus, the actual one, started to differ a little bit from what Newton's law predicted it should be. So this is a problem, right? This is a crisis. What are we going to do about this? Physicists were very concerned. Astronomers, physicists, very concerned. Maybe Newton was wrong, right? And getting more and more data. Yep, this is not matching what Newton predicts. Maybe Newton's wrong. Maybe there's something we don't understand here. But in the 1800s, a French mathematician named Urbain Le Verrier, he actually made some calculations, again, using Newton's law, and he said, you know what, people, this is not a problem. We're all good. We're all good. Newton's laws are still valid. It's just that there's another planet out there. And why don't we go find it, right? Y'all need to go look for this planet. And not only that, not only did he say that, he didn't only predict that there was another planet out there causing the problem. He said, hey, y'all point your telescopes over there, and you're going to find it. And so, guess what? People pointed their telescopes where Mr. Le Verrier told them to point them. And guess what? They did. They found another planet. They found Neptune, right? And so it's said that Neptune was discovered with a pencil and not a telescope. Because using Newton's laws, Le Verrier was able to tell astronomers where to look for Neptune. It's kind of a crazy story, right? So, okay, now we're all good. We've got Neptune added to the club, Uranus added to the club. Yeah, Pluto was discovered in there somewhere a little bit later. He got in the club for a while and then got kicked out. I don't know. We'll have to talk about that on another day. Okay, so we've learned that if I just drop a ball or a piano or a 57 Cadillac, neglecting air resistance, all of those objects will fall at the exact same rate, right? And we've learned that that rate is 9.8 meters per second squared. That's how fast they will accelerate, right? So their velocity will change at the same rate, 9.8 meters per second squared. If we're in a standard coordinate system where we call up positive, then we say, okay, this is down, so we'll add a negative sign, right? And then we can say, okay, well, this number right here, we're going to call that G, and so we can write this as negative G. Now, we have to be careful, though. This number right here, 9.8 meters per second squared, that's only G on Earth. If we were to go to some other planet, then it would be a little bit different. And so we have this equation here, so we can calculate what G on some other planet is. Here's our universal gravitational constant, again. So we have to be sure we're careful here between little g and big G, right? Big G is the universal gravitational constant. It's just a proportionality constant. It's the same everywhere in the universe. Little g is the acceleration due to gravity, and that depends on what planet you're on. And so we can think about the force of gravity from either the little g perspective, which is what we've done thus far, right? Thus far, we've used this idea of weight is equal to mass times gravity. That's the little g perspective. The big G perspective is that weight is equal to the force of gravity written like this. So we've got a big G perspective and a little g perspective. This perspective only works on the surface of a planet, if you know what G is for that planet. This perspective can work anywhere, right? Okay, let's try a quick example. A 60 kilogram person stands on each of the following planets. Rank order her weight on the three bodies from highest to lowest. And so notice we've got our three planets here. This one has a radius r, a mass m. This one has a radius 2r and a mass 2m. This one has a radius 3r and a mass 3m. Which one will have the strongest gravity at its surface? In other words, which one will have the highest value of little g at the surface? Why don't you give it a shot? I'll see you on the other side. Okay, so we're going to be using this equation right here. G is, little g is big G times the mass of my planet divided by the radius of my planet squared. Okay, so that means that for planet A, we'll start with planet A. That means that little g equals big G m over r squared. Okay. For planet B, we have G equals big G times 2m over 2r squared. Notice one of my 2's cancel, and I end up with 1/2 g m over r squared. Okay, so that one's smaller. Let's see about c. For c, we have so it looks to me like the greatest is A, next is B, and next is C. And PowerPoint agrees. A lot of times when I do this, students are a little tripped up because students just immediately assume the largest planet should have the largest gravity. But, it really depends on the density. Notice that these planets do not have the same density. Notice that the density of A is much greater than the density of C. And so that's part of why we can imagine that, how we can kind of wrap our brains around how is it that A has the greatest gravity at the surface, even though it's the smallest planet. And the answer is, it has the greatest density. And really it kind of comes, the density of the planet is closely related to this stuff. In fact, when Cavendish first discovered this gravitational constant, or not discovered, when he made the first calculation of this gravitational constant, it was heralded in the newspapers of the day as Cavendish measures the density of the Earth. Let's do one more example with this stuff, and we're going to kind of revisit something that's very similar to the first example we did, but now we're going to do it from the big G perspective. So when at the beginning of this lecture we did, how fast do I have to throw a rock to get it to orbit right at the Earth's surface, and we use the little g perspective for that. Let's kind of do the same kind of problem, but let's do it from the big G perspective. And since we're doing the big G perspective, we can answer this question not just for right on the surface of the Earth, where the little g perspective is valid, but for, anywhere close-ish to the Earth. So let's do that. Here's the Earth. This is the Earth here. Let's put a little E there. And, I don't know, here's a satellite, let's say. Okay? So there's my satellite, here's the Earth, and let's put this at a distance r away from the center of the Earth. So here's my satellite, here's my Earth. Much like before, right, we've just got this, this one force, right? Here's our free body diagram. And we'll call it the force of gravity now. We're in the big G perspective. We could reasonably call it the weight, but I like this better. Okay. Make positive towards the center of the circle, as we've been learning. Next step, sum of the forces in the x direction equals mv squared over r. And now we've just got one force, Fg equals m. Oh, wait, we need to back up here just a little bit, don't we? So this is Earth, and this is my satellite. Which mass is this? Ooh, I'm summing the forces on the satellite, aren't I? So this mass must be the mass of the satellite. That's how fast the satellite's going, and that's how far it is from the center of the Earth. Now, we'll plug in Newton's law of gravitation. And now, something interesting happens. The mass of the satellite cancels, right? That's interesting. That's interesting. One of our r's also cancels. And so now, much like I did before, we can solve for the velocity. Let's see what we get. We get that the velocity is equal to the square root of g, mass of the Earth, over r. That's pretty interesting, isn't it? So this is a super interesting result. This tells us that the velocity of some object in orbit around the Earth, and in this case I've used the Earth and a satellite, but this math works exactly the same if I'm talking about the Earth and the Moon, the Sun and the Earth, the Sun and Jupiter, Jupiter and one of its many moons, right? So this is really just one thing orbiting another thing, right? Notice what's interesting here. The mass of the thing that is doing the orbiting doesn't even show up, right? And so whether this is a satellite or Saturn or Jupiter, which all have very different masses, if they're the same distance from the Earth, they have the same velocity. That's pretty interesting. So the velocity of a stable circular orbit depends only on how far the orbiting thing is away and what the mass of the thing being orbited is. That's pretty interesting. So that's an interesting result. I like to do this math just because this is like a really heavy-duty result with historical significance that we came up with, that we learned how to do in 6 weeks of class. So I think that's pretty darn cool. Knowing that the period is defined as the amount of time for one complete revolution, we've defined that in a different segment, and that all the way around this circle is 2 pi r, the circumference, right? We could do a little bit of algebra on this in order to get this relationship here. So in this relationship, t is the period, amount of time for one complete revolution. R is the distance, so defined here, right? So these are all the same variables here. R is the distance between the centers of the two objects, and m is the mass of the thing being orbited. This relationship right here says that the square of the period is proportional to the cube of the radius. In other words, the period of a satellite's orbit, how long it takes to go around, depends solely on how far it is from the planet and the mass of the planet. That's pretty interesting also. This result right here is Kepler's third law. So that's kind of cool. This is one of the most important results in all of physics, and we have learned enough physics to derive this from first principles. I think that's pretty interesting. One orbit that's particularly interesting is a geostationary orbit, also known as a geosynchronous orbit. In a geosynchronous orbit, a satellite does not appear to move in the sky according to an observer on the Earth. And for Earth, the period of a geostationary orbit is 24 hours. Well, that's because the Earth rotates on its axis once every 24 hours. So the Earth's doing this. If I also get a satellite that orbits once every 24 hours, then guess what? That satellite doesn't appear to move in the sky, right? And so lots of communication satellites are geosynchronous, right? If you have Dish Network TV, then you probably have one of these little satellite dishes. What direction is it pointed? It should be pointed south, right? It's pointed south. Why? Because geosynchronous satellites are all over the equator. Because if I don't want it to appear to move, then it has to orbit right over the equator. Now, notice here that that orbit then, if it's going to have a 24-hour period, every one of these satellites is orbiting the Earth, obviously. That means every geosynchronous satellite is at the exact same height. And they're all over the equator. That's pretty crazy. In this slide, we see a map, a 3D map of where all of the known satellites orbiting the Earth are. And notice what we've got here. There's this ring right here that is just jam-packed. A lot more of them over populated areas of the planet, less of them over less populated areas of the planet. This ring right here are all of the geosynchronous satellites. They all have the same exact height, and they are all directly over the equator. And so that makes them appear not to move in the sky, because they're rotating right along with the Earth. Now notice here that if the radius is smaller, the period is smaller. Notice there's this gap here, right, where there's not a lot of satellites here. So these would be satellites that have a period less than 24 hours. Farther out, we've got satellites with a period of greater than 24 hours. And then, so there's a bunch out here, and then there's a whole bunch that are a lot closer, aren't there? And so these ones that are a lot closer, of course, these are going to have periods that are much less than 24 hours. The International Space Station orbits with a period of about 90 minutes. So you can see that it is much closer to the Earth than these geosynchronous satellites. It's probably here in this cluster, this little cloud we see around the Earth. So these satellites all have orbital periods much less than 24 hours. Spy satellites would be here. Certain communications satellites would be here also. The global positioning, the GPS satellites, the global positioning system satellites, they also are much, much closer to the Earth. They're in this cluster right around the Earth. Anyway, pretty interesting picture, I think.